Today we're looking at, this is from the chapter 8 notes, the PowerPoint. Today we're looking at estimating a population mean. We're going to be doing confidence intervals for means now. We did confidence intervals for proportions in 8.2. Now we're going to do it for means. It's a little different, and you'll kind of see why once we get into this.
I don't think I have the chapter 8 PowerPoint. Bro, I wasn't here. I'm pretty sure we bought it when you were here.
There you go. For a while. It's all right. I handed them out one day last week. I think it was on Tuesday or something. I don't know. Maybe Wednesday. All right. So, estimating a population mean. Our objectives for this lesson. After this section, we should be able to state and check the random 10% in normal or large sample conditions for constructing a confidence interval for a population mean. Okay? The random thing still applies here. It's the same as it was with proportions. The 10% rule condition still applies here. It's the same as it was with proportions. That normal large sample condition, though, recall from chapter 7 that for a sampling distribution of a mean, sample mean, it's going to be approximately normal when your sample size is a certain amount, 40 or 30. 30. Yeah, 30, sorry. Greater than or equal to 30. Okay, n has to be greater than or equal to 30. That replaces having to check NP and n times 1 minus p being greater than 10. That's what we had to do with proportions. Now we just have to check the sample size is bigger than 30. Or, we know the population distribution is normal. Either the sample size needs to be bigger than 30 or the population distribution needs to be normal for the sampling distribution to be normal. Okay? So we'll have to check that. We're also going to explain how, today we're going to be looking at new distribution, t distribution. We're going to explain how the t distributions are different from the standard normal distribution and why it's necessary to use a t distribution when calculating a confidence interval for a population mean. We got to determine the critical values for calculating a C% confidence interval for a population mean using a table or technology. We'll be doing it with technology. Construct and interpret a confidence interval for a population mean, and eventually determine the sample size. We'll do sample size problems here with means as well, just like we did with proportions. We'll see how far we get with this today. All right, so when the sampling distribution of x bar, sample mean, x bar is the sample mean, is close to normal, we can find probabilities involving x bar by standardizing. That means we make them a z-value. We take x bar minus mu divided by sigma divided by the square root of n. Why is it sigma divided by the square root of n? Because recall that the standard deviation of the sampling distribution of a sample mean was this. It was your population standard deviation divided by the square root of the sample size. Okay, that's on your formula sheet for the sampling distribution of a mean. Okay, that's the standard deviation for that sampling distribution of a sample mean, okay? That's where that comes from. Okay, I hope y'all are paying attention.
Yes,
All right. We were able to use that, but we had to know that population standard deviation. Okay? There's the gist of it. The sampling distribution of x bar, it has a mean of mu, and it has a standard deviation of sigma divided by the square root of n. Okay, and we standardize that to that normal curve. When we don't know sigma though, look, we're trying to estimate the population mean. Does it make sense that, we're going to know the population standard deviation, but we don't know what the population mean is? You calculate standard deviation using the mean. So if you don't know the population mean, you're not going to know the population standard deviation. So we're not going to be able to use z. We're not going to be able to use z star as our critical value with confidence intervals for means because we don't know the standard deviation. We don't know the population standard deviation. Okay? We can estimate it using the sample standard deviation though. S of x. That's a new notation that you may not have recognized. When it, lowercase s sub x, subscript x right there, that means the sample standard deviation. Okay? Sample standard deviation. S of x. Sample standard deviation. Y'all are okay with my abbreviations there. All right. So we can instead estimate it using that. So what happens when we standardize that? What happens when we take x bar minus mu divided by s of x divided by the square root of n? The sample standard deviation. That doesn't give us z anymore. What does it give us? Question mark, question mark.
It gives us a t distribution.
It gives us a t. Yes, so when we standardize based on the sample standard deviation, S of x, our statistic has a new distribution called a t distribution. Okay? T distribution. I pity the fool that don't know their population standard deviation. Okay? Get that reference.
She failed automatically.
Alright, it has a different shape though than the standard normal curve. It is symmetric with a single peak at 0. That's similar. However, it has a little bit more area in the tails than the standard normal.
Longer.
Okay? It still kind of looks like a normal curve, but it's just got a little more area on the ends. The tails are a little fatter. I don't know how else to describe it. Okay? It's single peaked. It's just whereas the standard normal bottoms out towards the axis a little quicker, the T doesn't. It's got a little extra area down there. Okay? It's still a density curve. It still has a total area under it of 1, but it's a little bit different. Okay? Here's the T versus the standard normal. You can see there's a little more area in the tails. There's a little bit longer tails too. But it is pretty symmetric. I mean, it kind of looks a lot similar to the standard normal. Okay. So, like any standardized statistic, T tells us how far x bar is from the mean mu in standard deviation units. Okay. There is a different T distribution for each sample size, which brings into this term, the first time we have to talk about this, you're going to hear this term again from here on out. Specified by its degrees of freedom, DF. Degrees of freedom. It has something to do with the sample size. We'll talk about how to figure out what that is, the degrees of freedom. Okay, we won't really get into exactly what the degrees of freedom are because that's a little bit beyond what this course is. It involves calculus. Just saying, but we won't really get into that. But it is the degrees of freedom. We'll talk about what that is right here. So the T distribution in degrees of freedom. When we perform inference about a population mean mu, using a T distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size. Don't ask me why, please, because I really can't tell you why, and getting into that reason will take us a while. For a T distribution, the degrees of freedom is n minus 1. It's the sample size minus 1. Okay? So we'll write the T distribution with n minus 1 degrees of freedom as that. Lowercase t, and there'll be a little subscript, a number, and it'll be whatever n minus 1 is. Okay, so t sub 5 means the sample size was 4, well 6, because it's n minus 1. T sub 39 means that the sample size was 40. Okay, you get what I'm going with that?
What's the rule?
Oh,
The degrees of freedom is n minus 1, your sample size
Okay.
minus 1.
Okay.
The why, I don't want to get into.
Okay.
I'm sorry.
I get it now. I understand.
Okay, it's all right. So draw so you're going to draw a simple random sample of size n from a large population that has a normal distribution with the mean mu and a standard deviation sigma. The statistic has the t distribution with degrees of freedom n minus 1. When the population distribution isn't normal, this statistic will have approximately a t sub n minus 1 distribution. It'll have a t distribution even if the population distribution isn't normal. It'll be approximately a t distribution. If it is normal, it'll be an exact t distribution. But if it's not normal, it'll be approximately a t distribution. So we get to use this regardless of whether the population is normal or not. That's if the sample size is large enough. Okay, of course. If the population distribution isn't normal, the sample size needs to still be bigger than 30. Okay, 30 or more. So when comparing the density curves of the standard normal and the t-distributions, several facts are apparent. The density curves of the t-distributions are similar in shape to the standard normal. I already talked about that. The spread of the t, though, is a bit greater than that of the standard normal. T-distributions have more probability in the tails and less in the center. So it's almost like the peak is a little lower in the center too. Because we're going to put more area in the tails, the peak is going to go down a little bit. Okay, it's going to be a little bit lower hill in the middle than a normal curve. And as the degrees of freedom increase, the t-density curve approaches a standard normal, though, ever more closely. As you increase the degrees of freedom, it will become more and more normal looking. Okay? All right, so what critical value T star from table B, which we're going to use a calculator to do this anyways, but should we use if we want to construct a confidence interval for population mean in each of the following settings? A 95% confidence interval based on a simple random sample of size n equals 12. Hold on. Okay, so here's what we're going to do. I just had to make sure that I was right on that. I forgot to check that this morning. So, if we want to do that, simple random sample of size n equals 12, let's go to the calculator. Hello. Yes.
Send me a text message just so I'll do it.
Yes, I will. No problem. Ansley, take all your belongings, you're leaving.
Is there the whole block?
I'm sorry.
Is it for like COVID?
I don't know. They didn't tell me.
Ansley, Miss Crow called me and asked me who I walked with in PE.
And why did Lindsay leave?
So you might get an early vacation.
Yo, why'd Lindsay Spurlock leave though?
Bro, I've
Lindsay's
already
furloughed.
had COVID.
You ain't got no COVID.
I know I don't have it. I've already had it.
They're gonna
That
quarantine
just
you.
makes me mad.
And then I'm making me
I mean, I'm still going to spring break, and I'm still doing my birthday stuff.
Yeah.
No one's
I mean, they
stopping
can
me.
quarantine at school, but.
I'm just not coming to school.
And you get an excuse. Someone cough on me.
I wish my desk was over.
I'm over here, Olivia.
I'll come over there.
I wish my
just
desk
for
was
you.
over like 2 oranges.
I'm far enough. I'm close enough.
All right, guys, back to
School's gonna
this.
be fun without you.
Bye,
All right.
guys.
But-
All right, so
I'll see y'all
Hey,
later.
you should move me sometime.
Okay. Bye.
I'll see you on it.
If we think about it,
Be careful. Love you.
Yeah, fun.
alright. So if we think about this, we want to find the T star value. We're going to do it the same way that we found the Z star value. We're going to go into the bars menu. So we go second bars. With Z star, we used inverse norm. Do you see something that jumps out at you like, I bet we used that one? For Z star, we used inverse norm. How are we going to find T star?
Repeat the question.
Yeah,
Okay.
I'm sorry. That's what I was trying to think in my head.
For Z star, we used inverse norm, right?
Okay.
Right.
So for T star, guess what we're going to use?
Inverse norm.
No.
Invert T.
Oh,
Inverse
there's the T there.
Hey, inverse T, number 4.
Thinking. Hold on, I'm just
Okay.
That's what I was thinking, but I didn't wanna say it.
Me too.
Well,
I
say
didn't want
it.
to look stupid.
I wanted, yeah, I was.
Alright, now, inverse T, the first thing, your calculator will look a little different because it'll have the fancy template, okay? It asks for the area, okay? Well, we find that the same way we found the area before. What was our confidence interval, confidence level again, sorry?
Low.
No, it was a certain percent, come on now.
0.1. Oh, like numbers, like the numbers that were. It was
90.
Yeah, 95.
Was it 95? 95?
95.
Look at the slide.
Okay.
Y'all are not paying attention.
I didn't know it was almost 95.
Yes, 95. Okay, so 95. So 95% goes in the center. So we need to find it the same way. We're looking for the T value the same way that we did, the same way we did before. We need to find that, really we'll look for this one, but just like we did with Z, this will be negative T star. This will be positive T star. We'll take the positive T star again. Okay. How much, if 95 is here, how much is here and here? How much will go here? 95% is on, 95% of the area is here. 2.5%, right? It'll be 2.5 here, 2.5 here to add up to 5 in order to make up the 100% with that 95. So it'll be 0.025 again. Okay, now your calculator, it asks for the area, so that's what you're going to put for area, 0.025. But then it asks for the degrees of freedom. How do we find the degrees of freedom again? We just talked about it. Literally on the last slide.
Is it the T equation?
Nope. It was the degrees of freedom.
It's in minus one.
It's n minus 1. N's this. What's
I didn't know
n?
that's what- I didn't know that was the term for it.
Nope. N's the. I don't think it tells you that in there. Come on, guys. Y'all should know what little n is by now.
What? I mean,
In this case, in this problem, even if you tell me what it is in this problem, that's fine. Look at the problem we're looking at right now. What does it tell me n is equal to?
But it's 12.
12?
It's the,
It's the what?
is it the random samples of
It's the sample size. So it'll be that simple random sample of size what? What was our simple random sample size?
it? It's 12.
12? So the degrees of freedom will be n minus 1. So what do we put in for the degrees of freedom?
11.
11. Okay, you always go down 1 from the sample size. Sample size is 12, degrees of freedom is 11. For T distribution, let me say that. You'll see degrees of freedom will also have something to do with another distribution that we talk about later on. There's still one more to come. At least one. I don't think there's another one. Okay, so we do that. We do 11, and then we go to paste. It should paste this to your screen then. on your calculator if you're doing this with me, and then you hit enter. It takes it a minute. Okay, for whatever reason, the inverse t sometimes takes a minute to calculate, so it may stop there and think for a minute, then it gets it. Okay, so we get our t star. This is negative t star. So positive t star, it's still symmetric. The t distribution is still symmetric. So by symmetry, positive t star will be the positive of this. So we use 2.2. I guess you could do 2.20 or whatever. Okay?
So do you need to round it to a certain place?
They, for whatever reason, a lot of times I see them round to 2 on the critical values, whether it's Z star or T star in confidence intervals, but you could do 4 like we've always done. You could put 2.201, because you round to 4, this 8 around that 9 up, which would make that 1. So if you wanted to put 2.201, that'll just make your interval more accurate if you do 4 decimal places. All right. So we still have to draw the curve to kind of make sense of the area. We still do that the same way that we did with Z star. The only thing different with T is the degrees of freedom, and it's n-1. With inverse norm, you had to put the area, and then you had to put basically the mean and the standard deviation, but since we don't know the mean, and we don't know the standard deviation, we don't have to put those. Okay? So it's a trade-off there. You just have to deal with this weird thing called degrees of freedom. All right. So they find that to be 2, so see they did round it like that 4 decimal places, so they get 2.201. So that desired critical value is 2.201 T star for a 95% confidence. Just like with before, any 95% confidence interval is going to have that T star value. You'll start seeing some of the same T stars come up, just like we did with Z stars. Okay, 1.96 came up a lot. Okay, in the problems. Now, that's where they'll mess with you and ask for a random other confidence interval, like calculate a 93% confidence interval. The typical ones are 90, 95, and 99. No, I'm just saying, those are the 3 most common ones. All right, we can do it again for a 90% confidence interval. Random sample of 48 observations. Okay. If we do that, we use inverse T. If 90%'s in the middle, how much is on the ends? 90%'s in the middle of the curve. How much will be on each end? 5, right? Because they'll have to add up to 10. So our area will be 0.05. What's our degrees of freedom? 47. Good job. We type that in. We get our T star, which this will come out to be negative T star. So if we want T star, we'll make that divide, we'll make this positive once we get it. -1, so you'll get positive, once you make it positive, you'll just make it positive because of symmetry. You'll get positive 1.67.
Do you have to round all those up, like that 9, like that
I always like to do 4 decimal places. I bet they do 3. They might do 3.
You just run the last one of that you,
I go 4 places after the decimal point.
and you just touch that one?
The next number is 2, so that's not gonna round this 9 up.
Okay, I didn't know if you.
If it was 5 or more out here though, that would round that 9 up, which would end up making that an 8.
Yeah, that's what I'm saying.
On that last example, that's what happened with how we got 1 there on the end. Okay, but normally you're rounding this one up, but it just so happens if your last digit's a 9, then that might potentially round up the next number, the next place back up. It starts a chain reaction, sort of. And it's really bad if there's a bunch of 9s, then it gets very confusing. Questions? Alright. Just wanted to practice some with doing that. Looks like Abby could delete us. I hope the thing doesn't just malfunction. Alright, so then they got that value, 1.684. What did we have? We had something different, didn't we?
We had 1.6779. See, like they rounded up.
Hold on a minute.
I think that's what it was. I don't care about
Oh, don't worry about it. Our estimate's better than theirs. They use the table. The table only has certain degrees of freedom, like 30, 40, 50. So like they had to go with 40 to be more conservative, to help not throw off their interval as much. But we have an even better estimate using the calculator. So our answers are going to be different than theirs. Just FYI. But we're better. Okay. As with proportions, you need to check these important conditions. Random, it needs to be a random experiment. You have to have a random sample, something. Well, random sample or randomized experiment. Look for that in the problem. Little n does need to be less than or equal to 1/10 of capital N. Capital N is your population size, so your sample size needs to be less than 1/10 of your population size. If your population's 1,000, then your sample size doesn't need to be bigger than 100. Okay, that's the 10% condition. You also need to check that
Are
you back?
Yeah.
What'd you tell them?
If I got it, like if you said that I don't have
Were they gonna try to make you quarantine?
to. She was pretty clear about it.
All right. So you have to check that for normal or large sample, either the population has to be a normal distribution, it has to tell you that in the problem, or your sample size needs to be bigger than 30. If the population distribution has an unknown shape and n is less than 30, we can use a graph of sample data to assess normality of the population. But do not use T procedures if the graph shows strong skewness or outliers. That's doing a normal probability plot. We haven't talked about that in a hot minute. Okay, we might have to go back and revisit that at some point. We won't get into that right now though. Okay, but that's what that's talking about. You plot your sample data and look to see if it's kind of normal. Okay. All right, so when the conditions for inference are satisfied, the sampling distribution of X bar has roughly a normal distribution. And because we don't know sigma, the population standard deviation, we estimate it by the sample standard deviation S of X. The standard error of the sample mean then is S of X divided by the square root of n, where S of X is the sample standard deviation, and it describes how far X bar will be from mu on average in repeated simple random samples of the same size n. To construct a confidence interval for mu, replace the standard deviation X bar by its standard error in the formula for a one sample Z interval for the population mean. And use the critical value from a t-distribution with n-1 degrees of freedom. So we replaced Z star with T star. We replaced that square root that we had before with S of X divided by the square root of N. Okay? So our new confidence interval, remember the general formula, statistic plus or minus critical value times the standard deviation of the statistic. Okay, we talked about that before. That's the general formula in words. So here it'll be X bar, sample mean, that's our statistic, sample mean, plus or minus T star times S of X divided by the square root of N. Honestly, I think this formula looks nicer though than the proportion one. Really. The only thing you missed, Ainsley, is we talked about how to find T star
How do you find?
in second bars. You go to second bars, right below inverse norm is inverse T. Yes,
Backward.
yes, and it asks for the area and the degrees of freedom. Unlike the inverse norm, you can't do center on this one, so you have to do it the way you do it.
Yay.
So the area, you put the area to the left. You do it the same way that we did area for Z.
Okay. That'll be fun, I think.
Okay?
Yeah.
I'll research it and see if there's a way to get it to do center, but I'm not gonna make that like a top priority, but you may have to
No,
do.
you're fine, I can do it.
So like, we did it for a 95,
Okay.
so that means 2.5 would be the area, 0.025, because you'd have 2.5 on each end, right?
Okay.
And then the degrees of freedom, we did it with, we had a sample size of 12, so our degrees of freedom would be 11, because it's always 1 minus. So you put 11, and then we got like,
-2 or 2.2.
yes,
Whatever.
that's what we had, 2.201, I think, is what, when you round it. So, questions? So the one sample T interval for a population mean, that's the kind of interval you'll calculate. So when you start to do one of these problems, you need to state what you're doing. Are you doing a one population Z interval for a proportion, or a one population T interval for a mean? That's the two options for this chapter. Are we doing it for proportions? We're doing Z. If we're doing for a mean, we're doing T. Okay? Now, it's similar in both reasoning and computational detail to what we did with proportions. So our interval, when the conditions are met, of course we check conditions, but when they're met, a C% confidence interval for unknown mean is X bar plus or minus T star times S of X over square root of N. Okay? This is that standard error of our statistic. Okay, remember the standard deviation of that sampling distribution was sigma divided by the square root of N. We don't know sigma, so we're going to use sample standard deviation divided by the square root of N as our sample error there. And this gives us our interval. T star is the critical value for the T sub n minus 1 distribution with C% of its area between negative T star and positive T star. That area is in the middle, like it was with Z. Okay? All right, so an example. One sample T interval for mu. We may not get to have any work time today. I may have to give you all work time tomorrow.
Please.
All right, so environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhaust from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxides. Researchers collected data on the NOx levels in grams per mile for a random sample of 40 light-duty engines of the same type. The mean NOx reading was 1.2675 and the standard deviation was 0.3332. So construct and interpret a 95% confidence interval for the mean amount of NOx emitted by light-duty engines of the same type. Okay, so let's do this to the side over here. As we're looking this on slide 12. Let's first state what we're doing. What are we doing here? What kind of interval are we going to do? Kind of tells us right there. We're going to do a one sample T interval for mu.
Yeah.
Okay, one. It's really you can write it this way, a one even population T interval for mu. Yes. Oh, I thought you raised your hand. Here, sorry.
What?
I thought you had your hand raised.
You're welcome.
Does anyone know what we're having for lunch?
No,
Come on.
I'm pretty hungry.
You're hungry
But I'm
too?
starving.
I'm about to start eating all my snacks.
The only thing I have is skinny.
I have 2 packed of
Do you know
cookies.
what's for lunch today, Mr. Crabtree?
No.
I haven't looked lately to see if they put the.
Do you bring your lunch or do you eat here?
I usually eat here.
Me too. I bring
Um,
snacks.
How are your cats?
Oh, wow.
Good.
His cats
Thanks
are
for
good.
asking.
I was like asking about the cats.
My inside one's probably at home right now, sitting in the window watching the birds eat.
Probably laying in the sun,
Mm-hmm.
sunbathing.
Mm-hmm.
I can understand.
All right. So we're check our conditions. Is it a random sample? Did it tell us that?
No. Yes, it did.
Or a random sample?
It did. I just didn't.
I almost always, when I'm reading the question,
How was?
underline the word random sample, just so that sticks out. You already know that it's a random sample. You don't have to check that anymore. Okay? Hold on just a minute. I'm gonna sneeze here.
Bless you.
No, maybe not. Alright. Alright, so it did come from a random sample. The sample is random. I always like just writing that if it's a FRQ. Takes 1 second, a couple seconds there to write that little sentence. The sample is random, so that takes care of the random condition. Alright, next we need to check, is the sample size less than or equal to 1/10 of the population size? Our sample size N is 40. Do you think that there are more than 400 light duty engines out there?
I don't even know what that is.
Like trains.
But yeah.
That's what I thought.
You thought what?
I thought of trains, like light duty
I
trains.
think it's like in cars.
Oh, okay.
Then yeah, there's definitely.
Yeah, there's more than 400 light
More than
duty
40.
engines out there. Now there are heavy duty engines on those like big trucks,
Heavy duty.
okay? But we're talking about light duty, smaller
That'd be like
vehicles.
cars.
But it's probably more than 400 of those, surely, right? So the 10% condition,
Heavy duty.
we can assume
That's a heavy duty. Light duty. Heavy duty. You're a heavy duty? Duty heavy?
there are more than 400 light duty engines. So that checks off the 10% condition.
Where is he sitting?
And our sample size is 40. So it didn't tell us in that problem that the population distribution was normal anywhere, right? I don't see it. Y'all tell me if I'm wrong.
No, it didn't.
It didn't, but our sample size is 40. And what's the cutoff for, if it's not 30 is the cutoff, so 40 is definitely bigger than 30. So little n is greater than 30. So we can assume normality and the sampling distribution. Okay, so we've checked our conditions. Now we're ready to calculate T star. Inverse T. We're doing a 95% confidence interval. Now the one thing about T is you will get, yes, you get the similar values for your levels of confidence, but actually no, you don't in a way, because your degrees of freedom may end up changing all over the time. So T is going to have I said that wrong earlier. I was wrong to say that, guys. You're actually going to get varying values for T star for different, even for the same level of confidence, because your degrees of freedom will change because your sample size changes from one thing to the next. Okay? What are my degrees of freedom real quick here? Just so I have them. If our sample size is 40, what's my degrees of freedom?
Is it 39?
39, it's one less. Okay, so our 39, oh wow, we're 36, sorry. 39. So inverse T, if we're doing a 95%,
It's
What's-
0.025.
yeah, 0.025. So our area is 0.025. Degrees of freedom is 39. So we get T star to be approximately, once you do that on your calculator, second bars, inverse T, 0.025. Degrees of freedom is 39. .0227. 9 rounds at 6/7. You get a negative of that, of course, but you make it positive. Okay. So our interval will be, whoops, not T. Our interval will be X bar plus or minus T star times S of X divided by the square root of N. That's our formula for the confidence interval.
So that's the formula for comp.
Yep.
Of a mean, right?
For
They're
mu,
gonna come on
yes.
the intercom and dismiss us, are they?
No, they won't, so I have to dismiss you. We're gonna get this problem done real quick. We'll take like a second. Okay, tomorrow we'll have a work day. Alright, X bar plus or minus, I'm sorry I've talked the whole time.
No, you're fine.
Alright, X bar plus, I hate being a lecturer the whole time. I was interrupted 5,000 times.
Yeah, you have.
Alright, so,
10 minutes.
X bar, what is our sample mean here? Tells us that in the problem.
The simple mean is it 1.267?
Yes, the mean Knox reading, that's from the sample. So that's gonna be 1.2675. Plus or minus our T value, 2.0227. Times our S of X, that's the sample standard deviation, which is the 0.0332.
Yeah.
Divided by the square root of our sample size, which is 40. And that's how we're going to calculate that. How about I'll let you finish this one? Finish this one for me for homework.
Yes.
Okay.
Finish this problem right here. I've walked you all the way to almost to the answer. Give me the confidence interval and try to even put it in, write a sentence in context. Try that too. You can do that. Homework tonight, finish this one in context, please.